I get many questions about the TSC, and over the years I've been interviewing people, and everybody says that they know how to use. And um, I just wanna make some remarks about how to use the TSC, and see what happens when different implementations are made, because there is not a single way to read the timestamp counter. There's many of them. Um, I just want to start with a few, with one example, and comment on top of it. So let's create a few implementations of the TSC. Um, Let me include first the stdint header, because we're gonna need it for the integer types. Alright, so the first type of so the TSC function has this prototype. It's I want it to be an inline function that returns a unsigned int 64. The first implementation that people think about is this one. Let's call it the let's call it xtsc. So what you do is you create two variables, 32-bit variables, and you create a function that calls the read TSC. This function is going to our DTSC instruction is gonna spit out a 64-bit number, but it's gonna be divided between the A and the D register, 32 bits into each one. This is a legacy of the 32-bit architecture we had before, 64-bit. But this instruction still works this way, and we have to carry on due to legacy for historical reasons. So I'm saying that the output is going into the low. The output of the A register is going to the low, and the output of the D register goes into the high local variable. What I'm gonna do then is I'm gonna OR the result of low with let's convert to 64. Let's cast to 64-bit high and shift it 32 bits. And this is it. This is the standard implementation of the read TSC. To test it, let me create a main CPP. I'm gonna read xtsc. Let me include the header that I created, and then let me print the result. Let's see if this compiles. Compiled with optimization turned on. Main CPP. Oh, main. Nope. What happened? Okay, so forgot one header. Wrong place. And this is print. Okay. Alright, so the TSC was read, and that's it. I want to look into the optimization and what. So let me add some debug information, and let's disassemble this main into, let's call it main X TST. Right. Here, the main routine should be here. Okay, we can see our TSC, the move. Oh, this move is actually interesting because we read the TSC. What the compiler did here, this move, this is apparently a no op, but what the compiler is doing is trying to zero the upper 32 bits of the A register, because EAX is the original 32-bit A register. Moving it inside itself guarantees that in the operation it zeroes the upper 32 bits, so you can do um, the shift and the OR. One interesting thing is that the compiler mixed up this line, which is gonna move some data from you see this byte is gonna move this byte from memory into the processor. So this is a good thing that's interleaved around these three lines, because it's going to increase the efficiency of the pipeline. These other lines, they are just this XOR EAX. EAX is basically zeroing, making the register A 0, because XOR of the same number of itself is 0. Moving the first argument of the print call to 1 as 1, and this is basically the std out, and this is the address of the string of this TSC format string. So that's what we expected. Let's now do one small change. Let's create a different function called, let's call another, let's make another one. Let's call it just TSC. This time, instead of calculating, letting the compiler calculate or join these two numbers, what I'm gonna do it myself. So my result is going to be 64 bits. I'm gonna issue RDTSC, but I'm gonna place some additional instructions. I'm gonna do the shift myself. I'll shift left D, and I'm gonna or register D with the register A. The result is going to be placed in register in the result variable, and no inputs, and I have to tell the compiler that I'm modifying the D register, because in this case here, that's what it tells the compiler. Here I don't have anything, but I do modify the D register by using the RDTSC function, which the compiler doesn't know. Then that's it, and I return result. Okay, let's save this, and here instead I just call TSC. Let's see what happens. Now we're gonna dump in, let's call main.t. Now let's compare the two. Let's see what happened here. Nothing, everything is pretty much the same. Some addresses change. And I guess this is obviously what's different. This one is the second. This is the X. This is the first one, and this is the second implementation. Yeah, this is border code. It's the same. What I want to do is I'm actually trying to realize. Okay, so this is the TSC. As we saw before, this stack pointer manipulation, it in the first case it interleaved with the other TSC calls, probably to increase the pipeline efficiency. Compiler does this kind of mixing, so the pipeline is better used. This is the preparing for the print call. This is the string, the format string. This is std out. It goes into di and si. This code is the same. Only in the second case, all my calls they are together. So the RDTSC, shift left, the OR, and here it takes the result which goes into the A register and saves into D because it's the call to print. I would say that this code is better because if I was measuring some section of my code, in this case, in the first case, I would have my TSC here and pieces of my TSC calculation here and here scattered throughout all the assembly functions, and this is actually the stack pointer manipulation. So yeah, we would not be measuring this. While here, all my code is in the same place. So given this, I think this is a much better implementation. So let's try to do some something useful with this. Let's try to do a loop, and obviously what I'm trying to do is let's say that I have a variable j less than a big number. Let's go to const enter it to t cycles, and let's do something here. Let's say that I have two random numbers, and I wanna see what's the cost of computing the remainder between one and the other. Right, so what we can do is actually put this TSC here, right, and doing V is equal to TSC minus V. So I get the difference. I can do this. Diff is equal to TSC minus V, and I can do um, mean diff is equal to a huge number, max diff is equal to 0, and then I do if diff greater than max diff, and min diff, Alright, so we in the end we say min max diff max diff, and we just ran just to see, this in stdlib. Not always remember where these functions are. So yeah, and then we should be good to go. Let's try to compile this and see. Obviously it didn't work. Mendiv Okay, what we are seeing is that with optimization, our code is 0, and without optimization this becomes a number. So it has a cost minimum between minimum and maximum. Why is that happening? Alright, so let's look the object dump of let's compile with optimization and look at the dump. Let's look for main. Right here. Oh, where is my TSC? There is no TSC. There is no TSC. And the reason is the compiler just here we go. It's doing XOR. So basically what's doing is zeroing the C and the D registers and just printing 0. This is 0. So the compiler just found that this TSC minus this TSC will always return the same result, and that's it. It didn't see that this function would return different values. So what we have to do is this. Let's see now. It's the same. I just decided that this would be 0. Oh, I put volatile in the wrong one. Let's see now. Now yes, if I run main, now it gave me a result. So the compiler, because I didn't put the volatile here, it just decided that this TSC, the result of this TSC would be the same as this one, and diff will always be 0, so it didn't even bother calling the function. If you place this volatile before, it informs the compiler that not to make any optimizations in this function and run it as is. If we look at the assembly code, we can see the TSC function right here and right here. This is what we want to see.